What's up guys? I've been working on an exoskeleton and what you just saw is actually the third iteration I've built. This is already a very big project and there's some progress from the past where I only used my smartphone to record, but I still want to take you guys on the journey so far and share my ideas and my progress. So instead of going straight to the new design, I want to take a step back and explain where I even started. There are many different aspects when it comes to an exoskeleton. Mechanical engineering, electronics, software, biomechanics, all these different fields come together in one big project. To keep it simple, I decided to split them into actuator design, the part which produces the torque, the force transfer design, the parts which transfer the torque to your body, the electronics like motor controller, and software. A couple of years ago, I started thinking about actuators, and the first question that crossed my mind was, how much torque do you even need? There are some studies and papers which try to answer this question, but after reading them and doing calculations using a mechanical model, I found out that I'm really not sure. There are different answers. So I decided on having at least 30 Newton meters of torque at the knee with a minimum RPM of 30, which works with most papers and calculations using my own body weight. The next question was, what kind of actuator? There are many different actuators someone can design. For example, the hacksmith uses pneumatics for his exoskeletons, which work great for big forces and on-off scenarios, but I needed a much higher level of precision. To keep it simple, I decided to only work with electrical actuators for now. So I started to design and 3D print different ones like compound planetary gears, simple belt drives like my wheelchair, cycloidal drives, and many more. I found out that every actuator was simply too heavy or too bulky, and most importantly shattered because I was focused on 3D printing my own actuator at first. However, even though I had not found a fitting actuator yet, I decided to build the first iteration using a compound planetary gear. I'm not going to explain the details of this gear set because that's a video on its own, but if you want to learn more, please check out Gear Down for What. His videos inspired me to use this type of gear set in the first place. I programmed a Python script which calculates the possible combinations for the needed gear ratio. It calculates all possible combinations and simply removes the ones which are physically impossible to design. This is the first exoskeleton I built. It kinda looks cool, but it happened almost 3 years ago and I only took pictures with my smartphone. As you can see, the parts were mostly 3D printed, which is why every time a different part broke during testing. But my goal was to learn and get experience as fast as possible. I knew that I needed a much more robust design for the second iteration, metal gears. I decided to connect a belt drive to a metal planetary gear set. Not only could it easily withstand the torque, but it's also super tough. However, I was surprised at how heavy the whole assembly was. The only way this actuator would work is with smaller aluminum gears designed for my specifications, but I don't have the resources to manufacture them, so I had to come up with a new idea. This is a strain wave gear. It is very light and has a high gear ratio relative to its size. Usually the motors are mounted directly to the gear like this, but I came up with a compact design using a belt drive to make it even thinner. Now this is my favorite part. Just in case something goes wrong, I have mechanically limited the range of motion from 90 to 180 degrees to prevent any movements which might lead to discomfort. I also use Hall sensors for redundancy and calibration. The actuator is then screwed to this aluminum plate where I can attach different mounting brackets. Now, of course, there are parts in this project which can be designed much better, but I only design aluminium parts in 2 dimensions like this, which means they can be laser cut and don't break my bank account. So I uploaded my files to a German manufacturer and got the parts within a few weeks. But the parts still needed to be drilled and tapped and prepared. At this point, I just want to apologize to my neighbors. I really try to make this as gentle as possible. I always go for a brushed look because it looks cool, and not because I'm trying to hide my imperfections. After 3D printing the other parts, I started assembling everything. It truly fascinates me when I assemble my own parts, because to be honest, they don't always fit together. At least they do in my head. The finished actuator weighs 1.1 kilograms and has a width of 42 millimeters, which is a big improvement. After designing the actuator, somehow the torque needs to be transferred to my body without any side effects. I designed these small brackets which can be strapped to my body like this. And after screwing these brackets to the actuator, the hardware is done. But before the first test, I want to talk about the electronics and software. I'm using an O-drive to control the motor. It has many features like PID control already built in, which saves me a lot of hours. I'm using Hall sensors instead of an encoder because with the high gear ratio, it is still very accurate. And I don't have the complexity of mounting an extra encoder. The O-drive is controlled by a Python script running on a Raspberry Pi. This script reads the sensors, does the calibration, and enters a loop where I can control the motor position with a PS5 controller. To power the exoskeleton, I'm using the same batteries I spot welded for my wheelchair. And that's it for the electronics. I used my smartphone to open a SSH session to my Raspberry Pi and started the script. After fixing the cables, I did the calibration and I was able to control the actuator with my PS5 controller. I have to mention that I'm an incomplete paraplegic with some control in my left leg, but because I have very strong spasms, I decided to use my left leg so I can try to relax my muscles. During the test, I realized that I can't properly transfer the torque to my legs like this. There was not only significant backlash, but the straps were too tight. I knew this from previous iterations and realized that for longer tests, this is not an option. Even though those parts look simple, it's very difficult to design something to work with your body without breaking your bones or cutting blood supply. In general, the solution to reduce pressure is to either decrease the force or increase the area on which the force is applied. So I came up with some 3D printed parts which spread the force to a bigger area. I also glued foam to it so the parts fit nicely and also feel comfy compared to hard plastic. These parts can easily be replaced by just unscrewing the old brackets. I like this design because I can try out different ideas for force transfer without redesigning everything. I think it turned out really nice. Here are some shots of the new design. The foam padding felt much better than just the straps, but there was still backlash between the exoskeleton and my leg, which needs to be fixed because the exoskeleton was still off by a couple degrees. I could still tighten the straps more, but I decided to not fully tighten them so it would still feel comfortable wearing. This is just another problem which needs to be addressed in future iterations. However, I was confident enough to do some load testing. I have a standing device which I use for daily workouts, and it's perfect to test the exoskeleton in a relatively safe manner. I only had one hand to properly support my upper body because I used the PS5 controller on one hand to control the exoskeleton. Also, I can barely control my hips, so I have to use my left arm to get in an upright position. But after some trial and error, I managed to put some weight on my left leg while leaning forward and picking myself up. I relaxed my arms and felt how the exoskeleton would hold my weight. It felt like I'm leaning against the wall and it didn't feel like it was breaking. Now that I'm in an upright position, I try different movements. Testing from flexion to extension while not supporting much weight with my arms gave me a good feeling of how the torque feels on my body. I also tested how rigid everything is by bouncing up and down. Even though it felt pretty safe, I still had trust issues. But let's talk about the exoskeleton again. I explicitly designed some parts to have flexion to a certain degree. It's really important to find a sweet spot between rigid, heavy, bulky, and flexible, lightweight, and compact. Anyway, during testing, the motor controller suddenly turned off and the exoskeleton left me hanging. Talking about trust issues. There's still a lot of work to be done, but that's it for this video. Thank you for watching and I hope you enjoyed it. I have to admit I wasn't sure how to package all the different content I wanted to share with you. There are a lot of things I didn't record when I started this project, and it's filled with many more small details. I still hope that it came together nicely because I wanted to show you guys the journey so far and maybe go into details in future videos. So please leave a comment if you are interested in the project and let me know what you want to see.